Hello everyone, my name is Hongfang Zhou. I am now a PhD student from S-Lab at Nanyang Technological University. I am presenting our work, AvatarCLIP, Zero-Shot Text-Driven Generation and Animation of 3D Avatars. Recently, text-driven generation has seen great progress, especially in text-driven image generation. OpenAI and Google has proposed DALL-E, DALL-E 2, and Imagine, which give fantastic photorealistic generation results. Part of the reason is that they all use millions of text-image pairs for supervised training. After seeing the progress in text-to-image generation, it is natural to think about text-driven 3D generation. However, unlike images, we cannot easily collect millions of 3D models paired with text from the internet. Luckily, recent progress in large-scale image text pre-training, namely CLIP, and differentiable rendering like NERF, provide opportunities towards the goal of text-driven 3D generation. Specifically, we can use differentiable rendering to render any 3D representations like mesh or implicit function. The rendered image is encoded by CLIP image encoder. Then the prompt is also encoded by CLIP. The optimization target is to minimize the cosine distance between the image and text features. Following this simple idea, many interesting works are proposed, like Dreamfields, achieves zero-shot text-driven general 3D object generation, and Text-to-Mesh proposes to edit 3D meshes in a zero-shot style. With this powerful tool, many opportunities are opened, including text-driven avatar generation and animation. Previously, this usually requires professional software and special skill sets, and is extremely time-consuming. Now, with the powerful differentiable rendering and large-scale pre-trained model, we propose AvatarCLIP. It can enable layman users to solely use natural languages to create their own avatars and animate them. The idea is pretty straightforward. We propose a two-stage generation pipeline. We first use the text descriptions of the body shape and appearance to perform the static avatar generation. Then we use the motion descriptions to generate motion sequences to drive the generated avatar. Now let's look at a more detailed pipeline. Given the body shape description, we first generate a coarse body shape. It is then converted to the implicit space by optimization. Then in the implicit space, we use the CLIP-guided optimization to sculpt the shape and generate texture. Finally, the implicit avatar is converted back to meshes and registered to simple for animation. For the coarse shape generation, we design a three-step algorithm. Firstly, we train a shape VAE as the shape prior. We use a parameter model simple as the data source. The VAE takes the coordinates of all the simple mesh vertices as input and output. After training the VAE, we perform clustering in the latent space of this VAE to get a codebook of possible body shapes. Then we retrieve the body shapes from the codebook that matches the text description with the guidance from CLIP. Specifically, for each entry in the textbook, we render the corresponding coarse body shape and use CLIP to get image features. Then we measure the cosine distance between the CLIP text feature and each codebook image feature and get the closest one as the result. The resulting coarse body shape will be converted from mesh to the implicit representation. Here we use an SDF-based neural radiance field, namely NEWS. It contains two subnetworks, one as the coloring network, one as the SDF network. By optimizing the reconstruction target, we can convert the mesh to the implicit representation, which is used as an initialization for the next step. In the implicit representation space, we perform shape sculpting and texture generation for the coarse body shape. In this stage, we need to make sure there are not large shifts from the coarse body shape, and we need to generate geometry and texture details at the same time. Firstly, as can be seen from the figure, in addition to the original color network CP and SDF network FP, we add another color network CCP for the texture. With this network modification, we can get four types of renderings. With the original color and SDF networks SCP and FP, we can render the white body image. It is used for the reconstruction loss, which is used to maintain the coarse body shape. Then by calculating the gradient for each spatial point on the SDF network, we can get the normal map. Together with random lighting, we can generate a colorless version of the model that shows its geometry. Finally, using the SDF network and the additional coloring network CCP, we can get a colored rendering of the avatar. Similarly, we use CLIP to encode the colorless and colored avatar renderings and minimize the cosine distance between the image features and the text feature. The idea is simple, but we need some other optimization tricks to make the idea work. The first one is inspired by Dreamfield. We randomly augment the background of the colored avatar rendering. This will help the optimization to concentrate on the centered object. The second one is semantic-aware prompt augmentation. This is to further improve the quality of certain parts of the avatar, like faces. For example, when we render a closed-up face of the avatar, we augment the appearance description to the face of someone. Similarly, when we render the back of the avatar, the prompt is augmented to the back of someone. This will greatly improve the quality of these parts, especially the faces. That's all about the static avatar generation. Let's move on to the motion generation part. In this part, we first use the given motion description to generate several candidate poses that match the description. These candidate poses are not necessarily temporally connected. Therefore, the next step is to use these candidates as references for motion generation. Finally, the generated motions are used to drive the avatar. Now let's get into the details of this stage. For the candidate pose generation, we first need to have some knowledge of possible human poses. To that end, we first train a pose VAE using the AMAS dataset. Then we cluster upon the latent space of the pose VAE to get a codebook of possible poses. For each entry of the codebook, we render the corresponding pose and extract features by CLIP. Given a text description of the desired motion, we use the cosine distance between the text feature and the codebook image features to get the most similar sets as the candidate poses. Then we need to use the candidate poses as references to generate a motion sequence. Similarly, we first need to get knowledge of possible human motions. Therefore, we first train a motion VAE using the AMAS dataset. The VAE training is pretty standard with a reconstruction loss and KL divergence. With the motion prior trained, the next step is to use the prior to generate motion sequences. Specifically, our optimization target is the latent code of the motion VAE decoder. We propose a three-part optimization target. The first one is the reconstruction loss. For each pose in the candidate poses and the decoded motion, we find the most similar pairs and calculate their differences as reconstruction targets. The second one is called the delta loss. Normally, we want the motion to be more intense or has larger movement. Therefore, this loss calculates the differences between neighboring poses in the motion sequence and intend to maximize the difference. Lastly, we want the motion sequence to be overall similar to the text description. Therefore, for each pose in the motion sequence, we apply the CLIP-guided loss to minimize the cosine distance. Next, let's look at some overall results of AvatarCLIP. Next, we show more results of the static avatar generation. Besides text descriptions of celebrities, fictional characters, or professions, we also experiment with the controlling and concept mixing ability of AvatarCLIP. For example, instead of the iconic black shirt of Steve Jobs, we can make him wearing a white shirt by inputting Steve Jobs in white shirt. Moreover, we can mix fictional concepts like alien or zombie with celebrities, which can give interesting results. We also make comparisons with several baseline methods. Ours perform the best among existing methods. Next, let's look at some comparisons of motion generation. Besides the qualitative results, we also perform detailed user studies as the quantitative results. For the static avatar generation, we study the mean opinion scores in terms of the consistency with texts, texture quality, and geometry quality. AvatarCLIP surpasses Streamfield or text-to-mesh by large margins. For the motion generation, we first study the quality of the candidate poses generated by several baseline methods. Then we study the final generated motion quality in terms of the consistency with text and the overall quality. In both studies, our methods clearly outperform baseline methods. Admittedly, there exist several limitations of AvatarCLIP. For the avatar generation, limited by the weak supervision and low resolution of clip, the results are not perfect if zoomed in. Besides, it is hard to generate avatars with large variations given the same prompt. For the same prompt, the clip text feature is always the same. Therefore, the optimization directions are the same, which leads to similar results across different runs. For the motion synthesis, limited by the codebook design, it is hard to generate out-of-distribution candidate poses, which limits the ability to generate complex motions. Moreover, due to the lack of video clip, it is difficult to generate stylized motion. Moreover, the use of pre-trained models might induce ethical issues. For example, if we input doctor, the generated avatar is male. If we input nurse, the avatar is female, which is gender biased. We think the problem originates from the large-scale internet data used for clip training, which might be biased if not carefully reviewed. Future works regarding the ethical issues of large-scale pre-trained models are required for the zero-shot techniques safe to be used. Moreover, with the democratization of producing avatars and animations, users can easily produce fake videos of celebrities, which might be misused and cause negative social impacts. That's all. Thank you for listening. Our codes and models are released on GitHub. You are also welcome to check out our project page to download our avatars.